Outcome. Outcome is the result of an experiment. Now we have two concepts here, experiment and outcomes. Example, a simple example of statistic experiment. Here's the example of an experiment. Tossing a coin. Tossing of a coin. Tossing describes a process. One pupil have a coin. The coin may be fair or not fair. And pupil toss a coin and it land up to the ground or land up to the table or land up in the floor. So people have to describe that process. There is a pupil have a coin may be fair or not fair, made by wood or made by metal or made by stone. We don't know, but we have to describe that process. And the coin affected by the temperature, the wind, the atmosphere, everything. We have to describe it. And it land up on the ground or table or floor. We don't know. We have to describe and we observe the result. The result, or we call it, is the outcomes. The head tail. And this experiment, there are two possible outcomes, head or tail. And head or tail, we call it the outcomes. Now, two concepts here is the experiment and outcomes. Now, do you understand experiment and outcomes of the simple example, tossing of a coin? Do you understand? If you understand, please write down you on the comment box, please. Do you understand my? You, okay. You, please write down on the comment box, you, please. Okay. If you don't understand, please write down no. I received many comments from you. Okay. Tossing a coin includes describe the process and observe the outcomes. Outcomes are result of experiment. Okay. And now we have the definition, sample space. The set of all possible outcomes. The set of all possible outcomes of a statistic experiment is called sample space and is presented by the symbol S. Or another word, sample space is the set of all possible finite grain outcomes of an experiment. Example, we consider flip a coin, an experiment, experiment flip a coin. So the sample space is the all possible outcome. Have only two possible outcomes, is the head and tail. And so we can describe by the curly brackets. Curly brackets is the sample space equal curly blanket head and tail to present for the sample space. And you see that sample space is a set. Is a set. So the theory of set in the algebra or calculus, you can apply to the probability. And each outcome of a sample space is called element or member of the sample space, and it can call the sample point. Each outcome is called sample point, or member is called sample point, and here's the data. And each X is a sample point or element, T is an element in the set theory, but in the statistics, people call it the sample point. Okay? And example, can I write? No, I can't write. Oh. I can't write. No problem. Difficult. Okay. Example 1.1. Consider experiment of tossing a dice. Now, not about the coin, a dice. A die have a six face from 1 to 6. 1 dot to 6 dot. If we are interested in the number that's shown on the top face, so the sample space is S1 equal curly brackets 1, 2, 3, 4, 5, 6. If we interested only whether the number is even or odd, the sample space is simply S2 is even and odd. So people call that S2 is the same is even space. Let I change. We are here. I would like to change the software because I cannot in the PDF. We stay here, okay? You see that? Even includes the finest grain outcome equal to 4 and 6, right? And odd equal the even 1, 3, and 5. So the set theory says that the union of even and odd, we have the sample space. Okay? Now, we consider a tree diagram. The tree diagram. We consider an experiment consists of flip a coin. When we flip a coin and then we flip the second time if a head occurs. If a tail occurs on the first flip, then a die is tossed one. To list the member of sample space, providing the most information, we construct the tree diagram figure 2.1. Tree diagram. What is that? What does it mean? I will show you. The various paths along the branches. Tree diagram have a node and branch. Of the tree gives a distinct sample point. Sample point is the element of the set, right? Of sample space. Starting with top left branch, we have the top left branch and moving to the right along first part. We get the sample point each 8. Indicating possible that has occurred on the two successive flips of the coin. Likewise, the sample point is T3, indicates the possible that the coin is so a tail, followed by a tree on the toss of the die. Okay. The first time we flip a coin, if head appear, we stop. If tail appear, right, we will flip a die. A die have the outcome is 1 to 6. The first outcome is a head or tail only, right? Do you remember? The first time we have a coin, we flip it. It have two possible outcomes, a head and tail. If head, the second time is we flip a coin. If it is tail, we flip a dice. That is experiment. Experiment is consist of many action or process. Process the first is a flip a coin. Flip a coin. The second, depending on the result here, the outcome here is the head. We flip a coin second time. If it is tail, the outcome is tail. We flip a dice. And here is a sample point.
Cô ơi, cô đang tắt mic ạ.
Cô đang tắt mic cô ơi.
Why who is muted my mic? Oh, sorry. If you understand tree diagram, please write down you on the comment box, please. You understand sample space, outcome experiment. Now I would like to know that you understand tree diagram. If you understand tree diagram, it includes the left branch move to the right branch. It has branches and nodes. Nodes show the outcome of each process. I received about 10 students. The other student, now we continue to do the example. Suppose 3 items are selected at random from a manufacturer process. I would like to turn off the neutral volume, the noise from the other device. Okay. Suppose that 3 items are selected at random from the manufacturing process. Each item is inspected and classified. Detective is D. Is a D is a detective, and non-detective is the N. Now we select 3 randomly at random. To list the element of the sample space providing most information, we construct the tree diagram. Tree diagram in the figure 2.2. Now the variable pass along the branches of the tree give the distinct sample point. We want to know the sample points. Starting with the first part. We're starting with the first part. We don't have the outcome of each experiment, right? We get the sample point. It's a DDD. It's a detect because we select three items. Okay, indicates the possible that all 3 items inspect are detective. As we proceed along the path, we see that the sample space here. The first item we choose randomly. It may be D or N. Non-detective. Detective is here's a node. Here's the left branches, left part. Here's the root. Okay. So first we choose randomly an item of a manufacturer. The product here is a detective or non-detective. The second item, here's the first item. The second item is outcome is D or N. If the first item is N, but the second item may be D or N. The third item is a DN. So sample point here, 3 items is DDD, 3 items may be DDN. If similarly, we have the other outcomes. And from this, we have a sample space is all the sample point of an experiment. Okay. From this, we have the sample space is here. From the example 2.1 to 2.2, we see that the sample point of a sample space is finite. So now we want to know where do we have the sample space, but the data point is large or in infinite number? The answer is yes. We can state by a statement or rule method because the sample space is a set. So we can write in by the formula. Sample space is all the data point X, that X is a city with population over 1 million. Example, Hanoi is a city that a population over 1 million. Ho Chi Minh City is a city that's population over 1 million. So it's can write out by statement. It is large, but not infinite. Okay. However, it can write out by rule. S is all the point X and Y that x squared plus y squared is more than 4. X and y is the real number set. Okay, so s here is the infinite data point. Okay, or we can consider example is S. It's a time we use in the inner day for study from 0 inner day for study to 24 hours, right? So it here is the real number set. So S is infinite. It's important for finite and infinite element of a sample space because it related discrete and continuous random variable in the next chapter. Okay. Now we have a new definition. It's an event. What is event? Event. Today we try to study sample space, event, continuous sample point, probability of event. Okay, and the other we will study in the next week. Event. Events. The event is an event is a specific element in the sample space. Event, another word. An event is subset of sample space. You know that sample space is a set, include elements, and any subset of sample space is called an event. Okay. So for any given experiment, we may interested in the occurrence of certain event rather than the occurrence of specific element in the sample space. The sample space have many specific elements. It here is the element. However, we want to know about the subsets of the sample space. So we call the event. Example, we introduce the event A is the outcome when a die start is divisible by 3. The event A is the die start is divisible by 3. So A equal 3 and 6. So 3 and 6 is a subset of the sample space. So A is called an event. Okay. So an event is a subset of sample space. Now please write down on the comment box. An event is a subset of a sample space on the comment box, please. Please write down an event is a subset of a sample space on the comment box, please. Can you hear me? I received the comment of Đặng Huy Hoàng. An event is a subset of the sample space. Received 3 students. The other student. You said that by COVID, we have distance at home and many computer, telephone have problem. And you know that computer have a 5-year guarantee. However, the time of a computer often is 5 years. When we use finish 5 years, it often have a problem or malfunction. Okay, so people give to us the sample space when we consider a lifetime of computer. So given the sample space S here is a T greater than 0, where T is the life in year of a certain electronic component, such as your computer. Then A is the component failed before the end of 5th year. You see that the computer have only 5-year guarantee. It's luckiest guarantee time. Often only 20 months or 24 months or 36, because people or manufacturer know that the long life of the computer only 5 years. So A is a T is an event because it's the subset of the sample space S here. Why people consider it? Because it related the profit they get if they assign the guaranteed time. And the sample space follows the set theory. Sample space S is a subset of S2. So S is called an event. And the null set is denoted by the symbol empty here, null set here, which contain no element at all, right? Sample space contain all the outcome. Reverse, the null set contain no element at all, but null set is same subset of S. So null set is called an event. Okay. For instance, if we let A is the event detect a microscopic organism by a naked eye in the biological experiment, A equal null set or null set because naked eye don't have microscopic organisms. It relates the biology, science in America, so they know clearly about it, but we maybe don't care. Okay, if B is the event of X is greater even factor of 7, then B must be the null set, since the only possible factors 7 are odd number from 1 to 7, right? Now we consider the relationship of an experiment. We have a relationship and operations. The relationship here is the complement of an event A with respect to S is the subset of all elements of S that's not in A. The complement of an event A with respect to S is the subset of all elements of S that are not in A. And we denote by A prime. Some course textbook is denoted by simple AC or A over bar over line. However, in this textbook, people choose the A prime to show the complement of event A. Example, let's R be the event that red card is selected from ordinary desk of 22 playing cards, and S be the entire deck. Then in complement of the event R is the event that the card selected from the desk is not red card. If it's not red card, it must be a black card. So R here is a red card, and R complement of R or R prime here is black card. Now, do you understand complement of an event? If you understand, please write down U on the comment box. If you don't understand, please write down N. I will illustrate by the example 2.6. Consider the sample space as is tool, equipment, heavy study, books, cell phone, MP3, paper, stationery, laptop. Now A is the equipment, includes book, stationery, laptop, and paper. And what is the complement of A or A prime equal? Is the all the element. It's a sub is all element of S, but not in A. Not in A, not in A, here, so, okay, not in A, here, phone, MP bar, not in A, right? Here, in A, stationery in A, laptop in A. So here, A prime is a cell phone, and three, oh, sorry, cell phone is a word together. Cell phone and MP3 in the complement of A. Now A is the 2, 4, 6. It's the event of even phase occur. Now B is a complement of A. It's in A, but it in S, not in A. So it is 1, 3, and 5, right? Now we consider another definition. Is the operation. The operations of the event. We have 3, often 4, however we study 3. It's union, intersection, and complement. Yeah, we have just studied complement. Now we continue to study intersection. We have the different operation. However, different can present by when we integrate complement and intersection. Now we consider flip a dice, and A is the even dot occur in the face of a die, and B is here, 2, 4, 5, 6. Now we consider both A and B will occur. On a given toss, if the outcome is an element of subset 4 and 6, A and B both occur, so it calls the intersection of A and B. Now we have definition. The intersection of two events A and B. Intersection of two and B denotes the symbol A cap B. Intersection B is the event contain all the elements that are common to A and B. Because sample space is a set, A and B is the event, are events. They are the subsets of S. So all the operation of the set theory you study in algebra or calculus in the first grade, first year, you can apply to the event. We have the intersection operation. we have the new concept. It's mutually exclusive or disjoint. Some books use mutually exclusive. Some books use disjoint. Why people use two concepts here? Disjoint often used for only two events, and mutually exclusive used for more than two events. When we finish definition, we have a 10-minute break. Now, I would like to tell you the difference of mutually exclusive and disjoint. Mutually exclusive, when we have a 1, a 2, 3 dots, again, we have n events. And disjoint we often use for the two events only. The definition of mutually exclusive of two events, A and B, if and only if A intersection B equal null set or empty set. That is no element in A and in B in common. Okay. Example. A couple television company offer program in 8 different channels, 3 of which is affiliate with ABC, 2 with NBC, and 1 with CBS. The other 2 are an educational channel and the ESPN sport channel. Suppose that a person subscribing to this will be turned on the television set without first selecting the channel. Let's A be the event that the program belongs to NBC network, and B the event that it belongs to the CBS network. Since a television program cannot belong to more than one network, that events A and B has no program in common. Therefore, intersection of A intersection B contain no program, and consequently, the event A and B are mutually exclusive. It's very easy. A intersection B equal null set, so we call that they are mutually exclusive. Okay. We have another example. A equal 2, 4, 6. B is 2, 5, 6. A intersection B equal 4, 6. The question, A and B is mutually exclusive. A and B is A and B mutually exclusive, yes or no? Please write down the comment box. Please. A and B are mutually exclusive. Are A and B mutually exclusive? Yes or no? Write down on the comment box, please. Okay, I received many it means 6 students. The other student, okay, now it's 8 o'clock in my computer. We have a 10-minute break. We will come back at 8:10. Now we break 10 minutes. They are not mutually exclusive. Very good. Okay, 10-minute break, please.
bao gồm nhiều du thuyền và các tài khoản ngân hàng ẩn danh giúp họ che đi sự giàu có và trốn thuế. Hiện hồ sơ mật này thì đang được Hiệp hội các nhà báo điều tra quốc tế Washington của Mỹ nắm giữ để phục vụ cho công tác điều tra ở quy mô toàn cầu. Thưa quý vị, một vụ rò rỉ tài liệu mang tên hồ sơ Pandora đã vừa hé lộ hàng loạt giao dịch và tài sản bí mật của những nhân vật quyền lực nhất thế giới, bao gồm hơn 100 tỷ phú, 30 nhà lãnh đạo thế giới và 300 quan chức nhà nước. Theo các chuyên gia, thì đây là vụ rò rỉ dữ liệu tài chính lớn nhất gây chấn động thế giới.
Hello everyone, can you come back now? The answer is A and B is not empty set. Intersection of A and B is not empty set, so A and B are not mutually exclusive is right. I received many solutions from you. Now the next operation is union. We have three operation of the event. It's union, intersection, and complement. We understand complement, intersection. Now next is union. The union of two events, A and B, denote the symbol A cup B. Is the event. A cup B is a subset of the sample space, so it is the event containing all elements that belong to A or B or both, right? A or B. Example, A have three elements A, B, C, and B have four elements B, C, D, E. So A union B is all the elements in A or in B. So it's A, B, C, D, E. Okay. The other example, please read by yourself at home. Now, if we pretend by calls the Venn diagram, A have a four element 1, 2, 4, 7. B have a four elements is 1, 3, 2, 6. And C have a four element 1, 3, 4, 5. So A union C equal the reason 1, 2, 3, 4, 5, and 7 have 8 elements, right? And B prime intersection A. B prime is mean in S, not in B. So it includes 4, 7, 5, and intersection with A. So it is 4 and 7. The reason and 4 and 7. A intersection B intersection C is here. Intersection is 1. And A union B equals 1, 2, 3, 4, 7, 6. Intersection C prime is 2, 2, 6, 7. So we have 3 elements, reason of 2, 6, and 7. Now, I hope that you studied about the set theory many times. You can understand clearly about the events, about the operations of events. The subsets, you know subset and equal, we study similar with the algebra set theory, okay? Here's the exercise for you to do at home. We have about 20 exercise at home about the sample space, event, operation of event. Next lesson about counting sample points. Do you know that sample point is the element of sample space? When we do statistics, the element of sample space calls the sample points. Now, counting sample points. We have a fundamental. The fundamental principle of counting. It often refers the multiplication rule. What is a multiplication rule? If an operation can be performed in any one way, and is for each this way a second operation can be performed in two ways, then the two operations can be performed together and one multiplication and two ways. If we can describe by another word. One big word can divide by two processes. The first process have n one ways, and the second process is n two way. To do the big work, we have to do n1 times n2 ways. So it holds the multiplication rule. Okay. Example. How many sample points are there in the sample space where when a pair of dice is thrown one, we thrown one pair of dice. The first dice have 6 ways, right? The first dice land face up in any one, have a n1 is 6 ways. For each 6 way, the second die can be lined up with n2 equals 6 ways. Therefore, the pair of die can land is n1 times n2. It's 6 times 6 equals 36 both ways. Okay? Do you understand multiplication rule? If yes, please write down U on the comment box. If you don't understand, please write down N on the comment box. Multiplication rule. It is a fundamental principle counting. From this rule, we can derive many theorems and many formulas. Do you understand multiplication rule? If you understand, please write down U on the comment box. Nice. I will take another example, 2.14. A developer of new subdivision of a prospective home buyers a choice of Tudor, rustic, colonial, and traditional exterior styling in range, 2-story and split-level floor plan. In how many different ways can the buyer order one of these homes? About the exterior style. So, about the exterior style, have a Tudor, rustic, colonial, and traditional. About the floor plan. Each have 3 types: range, 2-story, and split level. The first operation have 4 ways. The second operation floor plan have 3 ways. So we have 4, multiply with 3, so we have 12 possible outcomes. We have many examples. Please read by yourself at home. Now, general, we consider K operation. If an operation can be performed in any one way, if for each of these a second operation can be performed in any two ways, and for each the first two of three, first two third operation can perform in three ways, and so forth. The sequence of K operations can be performed in 1 and 2, and so on, and K ways. So here, general of multiplication rule, called generalized multiplication rule. And above the rule 1 for K equal 2, now a K general, okay? You can read by yourself. Now we have the concept permutation. What is a permutation? We studied in high school. Now I remind you. A permutation is arrangement. It's an arrangement of all or part of a subject, part of a set of objects. Now, the question, if the set of an object, the set of object is A, B, and C. Now, what is a permutation? If S is A, B, C, set of object here, object is A, B, C. Set of the object is a sample space like this. Okay, permutation is an arrangement of all the objects of this set. So permutation, I show you one permutation. Is A, B, C. A, B, C here is called permutation because it arranges all the elements of S, right? So we have another permutation. It's A, C, B, B, A, C, B, C, A, C, B, and C, B, A. That's all. Because you see that's the arrangement. ABC is different position and different objects, right? So the question, how many permutation of the sample space at here? We apply the generalized multiplication rule. When we arrange a permutation, the first position have three ways. The second position is another element different with the first, so have only two ways. And the last different with the first and second element, so have one way. From this, we have a multiplication ruler is N1, N2, and N3. So we have 6 permutation. Permutation is arrangement, it's here like this. But the number, you remember the different, the number of permutation is 6. Several students tell me that, oh, a permutation is 6. It's not true. Permutation is arrangement of all the object of the sample space here. It's like this, it's permutation. 6 here indicate for the number of permutation. right? Do you understand permutation? If you understand permutation, please write U on the comment box. I received only one answer, second answer from Thang and Kian. Our class have a lot. Please write down you quickly. I will change to another concept. Please write down by your own word to on the comment box to confirm with me that you understand permutation. We have a definition, it's factorial and a factorial. And a factorial is denoted by n factorial here, okay? N factorial equal n minus 1 times n minus 1 times it is 3 dots times 2 and times 1. And space case here is 0. 0 equal 1. Okay? So the number of permutation of n objects, a number of permutation of n object is 3n factorial. And we denote we have the concept then the new sample space now is 4 elements A, B, C, and D. Okay, so the permutations of subsets of set sample space S here is the 4 factorial. So we have a 24 permutation. Now we consider only permutation of that or possible take 2 letters from S. Only two letters. Permutations that possible to take 2 letters at a time from 4. How many permutation of 2 from S? So it is AB, AC, AD, BC, BA, BC, BD, CA, CB, CD, GA, GB, and DC. You see that is a 2 element only. It's it only. Let's I see here is a X and Y. Permutation of 2 letters. X can take from S and Y can take from S here. How many ways to choose X? 4 times, right? 4 times. And 1 equal 4. And how many ways to choose Y here? Because X and Y permutation is different or distinct value. So N and Y must be different with X. So N2 equal 3 only. So we apply multiplication rule. We have N1 and 2 equal 4 times 3 equal 12. So we have 12 the 4 distinct objects taken 2. So general 2 is here is a 12. So in general, and the distinct object taken L at a time can be arranged in n minus 1, n minus 2, 3 dots, and minus r plus 1. And we present by the symbol npr. It equals n factorial over n minus r factorial. It here is n distinct object taken R. Okay. From this, we have the theorem. We have just proved the theorem 2.2. The number of permutation of n distinct objects taken R at a time is NP. P is the denote for permutation. NPR is the n factorial over n minus r factorial. Example, in 1 year, 3 work, research, teaching, and service will be taken to a class of 25 graduate students in a statistics department. If each student can receive at most 1 award, how many possible selects are there? So we've seen the word distinguishable. It is a permutation problem. The total number of sample points is, we choose 3, permutation 25, 3. So follow this formula. We have this permutation. Here's the number of permutation of 25 graduate students. We have many ways to do it. Okay. The other example, please read it by yourself. Now we have the theorem. The permutation of n object arranged in a circle. You know that if it's not in circle, permutation of n object arranged, it is n factorial. However, in a circle, it's n minus 1 because the circle, the first element to choose position is the same with every position. Every position in the circle. When we relationship with another element, so it's the same. So the number of permutation arranged in circle is n minus 1 factorial. Okay. Example. So far we consider permutation distinct object. That is, all the object can be completely different or distinct. Observe, if we consider the S here is the A, B, and C. Okay. S here is A, B, and C. We assume that 3 students, student A, student B, student C, arranged in the circle table. How many permutation? 3 students arranged in a circle table. How many? We see that? Also, obviously, if the letter B and C are both equal X, B, C, we consider is the letter X. Then 6 permutation of letter A, B, C become AXX, AXX, XXA, XAX, XXA, and XXX. With only three distinct, because here's the same, here's the same, and here's the same. Therefore, with three letters, two being the same. So we have 3 factorial over 2 factorial equal 3 distinct permutation. With 4 different letters A, B, C, and D, we have 24 distinct permutation with A, B equal X and C, D equal Y. We have list only following distinct like this. Thus, we have 4 factorial over 2 factorial over 2 factorial equals 6 distinct permutation. From this, we have the new theorem. It's the number distinct permutation of anything of which n1 are one kind, n2 is the second kind, and nk is the k kind. It follows this formula. And factorial and over this. The difference. Here's called the theorem distinct permutation of anything with k different kind. We will use it for the binomial formula. Another example. Another example. In a college football training section, the defensive coordinator needs to have 10 players standing in a row. Among 10 players, there are 1 freshman, 2 sophomores, 4 juniors, and 3 seniors. How many different ways we can arrange in a row if only their class level will be distinguished? 10 players, 1 freshman, 2 sophomores, 4 junior, and 3 senior. So the different way arrange a row if only their class level will be distinguished. Follow this formula. It equals that. Sorry about I take a wrong example. The set here, if we give the position not circle, we have 3 factorial. However, because A, we can choose the first person in a circle. We have only 1 way. So the second have two students. The first we have 3 way, 1 way, because all the position in the circle is the same. So we have only 2 way for the second position and 1 for the last second. So in the circle, the the permutation is not 3 factorial, it moves to the 2 factorial. If we arrange row, we have 3 factorial. When the circle is moved to from 2 factorial, n-1. And here is a distinct line. Here's the apply of it. Okay? This formula helps us to understand more about the number of ways to partitioning of a set and an object into error cell with n1 element in the first cell and the 2 element in the second cell and so forth. Is a combination n1 and 2 follow this formula. Okay, where n1 plus n2 plus n error equal n. People call that is the partition of n set to error cell. Partition. Example. How many ways can 7 graduate students be assigned to 1 trip or 2 double hotel rooms during a conference? You know that 1 trip is 3 students in one room, and 1 room have 2 rooms have 2 students. So we choose 3 from 7, 2 from 5, and 2 from 2 left. So we denote by the 7, 3, 2, 2. So follow this formula. Okay? It's a partition. 7 students into 3 rooms. 1 room have 3 students, 1 room have 2 students, and 1 room have 2 students. Okay? Do you understand example 2.21? If you understand, please write down you on the comment box. If you don't understand, please write down no. I will repeat or illustrate more. Can you understand? I received 1 student with Mạnh Thắng tell me no, the other say you. I give you 30 seconds to write down your attitude. Can you tell me your point of view about the partition a set of n objects to error cells? I received another answer from the Ngô Mạnh Hùng say no. Thắng and Hùng say no. The other, please write down, please. Do you understand partition of n set to the object? You remember the multiplication tell us that if we divide the process 1 have n1 way, process 2 have n2 way, 3 dots, process k is nk. Here's the multiplication ruler, you understand, right? Now partition an object to k cell. It's the same 7 graduates, here 7 objects, divided in 3 cells. The first cell is 1 triple, it's 3 students. The second is 2 students, and the last is 2 students, right? So it equals that. The first, we have n, we partition n object, and we choose n1. And the partition of the room 2, we have only n minus n1 student, permutation n2, right? So forth, so on. We have we only have nk, b, nk. And what is this? It equals n, the first n, p, n1. You remember n, p, n1? Okay. N PR equal n factorial over n minus r factorial. Equal n factorial over n minus n1 factorial times here n minus n1 factorial over np Oh, I forgot that it's not B, it's a C. C. Partition without the replicative C. Here's the n1 factorial. It's here. N factorial over n minus 1 factorial and 1 factorial. And here's the second n1 n1 c n2. We choose n2 factorial for partition second. So it equals n minus n1 factorial over inside here equal n minus n1 minus n2 factorial and 2 factorial and so on. It's nk, k here is 1. So when we eliminate n minus 1 from here to here, so we have this formula. Okay. Now I will illustrate more about the 7 elements. 1, 2, 3, 4, 5, 6, 7. Here's 7 students. So it equals, I can write down it is 7 is a S. equal 1, 2, 3, 4, 5, 6, 7. Now partition to 3 room. 3 room 1. We choose the 3 students. 3 students from 7 students. 7, 3. Time with, we have only 4 students. So 4 students, choose 2 students for the second double room. And time second, C second. So it equals 7 factorial over 3 factorial, 2 factorial, 2 factorial. So we have 210. Okay. Now Hùng and Thắng, do you understand now? Please write down on the comment box or answer me. We don't have much time. Okay. Thắng is okay. Now Hùng, do you understand? Ngô Mạnh Hùng, do you understand now? Can you tell me? Can you hear me, Hùng? Okay, okay, thank you. Continue. What is the number of combination of any distinct object taken from R? The combination, we don't arrange. We don't consider the order of objects. So it's the combination N R equal this formula. I think that is familiar with you. The number of combination, to remember here's the number of combination of any distinct. The combination is familiar with all of you, so I don't show more. We concentrate on example 2.22. A young boy asked his mother to get 5 Game Boy TM cartridges from his collection of 10 arcade and 5 sport games. How many ways are there that his mother can get 3 arcade and 2 sport games? The number of ways to select 3 cartridges from 10. We have this formula. Choose 5 from any distinct object. Now choose 3 cartridges from 10. We don't consider about the order of the object. So it have a 120. The number of ways to select 2 sport games from 5 sport games. Number of ways to select 2 cartridges from 5 is the combination 5, 2. So we have 10. Using multiplication rule. And the 1 equals that, and the 2 equals that. So we have this way, 1,200 ways. Okay. Another example. How many different letter arrays can be made? How many different letter arrays can be made from the letter in word statistics? Here. How many? Here's the questions of final test. Let I show you the final test. The final test here. No, here's a resource. I have another. Let I remember. I don't remember much. Maybe this. No. Maybe this. No. Maybe. Not right. Here. Here is correct. Too many. There are too many. I don't remember. There are too many. We have too many tests, so I don't know exactly what is the. Is it here? You see that? There's a permutation, combination and permutation. Here's a sample space. Here's a complement. And statistic is not in this. I don't remember what is the name of it. Too many example. I don't remember. Here. How many ways to arrange? There are 3 ways to arrange MOM from the letter MOM equal MOM, OMM, MOO. So how many ways to arrange this character TICA-BHAN to the words? How many ways? So this for the moderator level, medium level. Okay, so it's the same. So theorem, we have only this, okay? But we have many exercises to practice the theorem. It's the way asks us how many different letter arrays can be made from the letter in the word Statistics. We're using the same argument as in the discussion in the theorem 2.6. In the example, we can actually apply the theorem 2.5. 2.5 here. I show you the relationship with 2.6 and 2.5. Is it here? From 2.6, we have a 2.5 the formula. And we apply to this problem, the example. So from 10 letter, we arrange the same here is 3S, 3T, 2 I's, 1 C, 1 S. So we have this here, 10 letter, 2 letter SD, 3 each time, letter I, AC each one, A and C each one. So we have the formula and we have this arrangement by this letter to the words. Here's 5,000, 50,000, 40, 100 different words. Okay? You do the 248 exercise. Now I have 10 minutes to give to you the probability of an event. The definition, the 3 lessons today, I have a miss with you about 15 minutes, so I can't finish the lesson 4 yet for this week. However, I introduce to you the probability of event in 5 minutes. Next week, I will illustrate more. So please do homework at home. You can understand clearly about the 3 lesson previous, about the sample space, about the event, and about the counting of principle of counting. And now the probability introduced. The probability of an event A is the sum of weight of all the sample points of A. Sum of the weight of all sample points in A. Therefore, we have a probability of the event A is a number greater than 0 and smaller than 1. We have a probability of M known set equals 0 and probability of sample space equal 1. And if we have A1, A2, and so on, here is called a sequence of mutually exclusive events. What is the mutually exclusive? I told you that the mutually exclusive have the same concept with disjoint, but mutually exclusive for many events, disjoint for only 2 events. It means that AI joy, here's a cap, AJ equal null set. AI intersection AJ equal null set. Okay, for all the I different J, we call that mutually exclusive event. Then we have a probability of union of infinite event equal probability of sum of each event. or probability of A1 union A2 union A3 and so on equal probability of each event, probability of A1, probability of A2, probability of A3 and so on. People call this definition as the probability axiom. What is axiom? Axiom is a statement we accept, not prove. And this definition was born is derived of Komogorov. It's a Russian mathematician in 1959. It means the history of this definition is only 60 years. People use probability long time ago, 6,000 years ago, as if science due to measure the field, the points in a Nile river. However, they don't have a probability definition. It's 1955 Komorov is a person who gives to us the definition. It's reduced the disadvantage of many other definition probability. Probability axiom have three axioms. The first axiom, for any event A, probability of A equals 0 and 1. And the second axiom is probability of sample space is 1. And here's the axiom 3. Probability of union of infinite. Remember, here's infinite events equal sum of probability of each event. When we finish example, we stop the theory section this week, and I will meet you on the morning of Friday this week. A coin is tossed twice. Here's the experiment, and we know that the outcome is here and sample space is here, right? Now the question, what is the probability that at least one head occurs? So what is the event A here? A is an event. At least one head occurs. So the coin is balanced. We assume that the coin is balanced. And each outcome is equally likely to occur. Therefore, we assign probability of W to each sample point. W in each sample point, it may be here, 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 here. So for W equal 1, so W equal 1 over 4. Each outcome has the same possible occur, equal chance. So it is 1 over 4. Here's the probability of W. So probability of W equal 1 over 4. And A, here's the event, have 3 outcomes. Okay, here, here, and here. Each one outcome, the possible chance happen is 1 over 4. So 3 outcomes. We have a 3 over 4. Here's the probability of A. Probability of A, you see that from 0 to 1. Sample space here. When we toss a coin 4 times, here's all possible outcome. So probability of X always equal 1. 4 over 4 equal 1. And we use Asian. A1, A2, and A3. Equal probability of A1, probability A2, probability A3. However, when we use it, we have to prove. However, in this textbook, we don't have the proof this. Maybe in the exercise lesson, I will show you the proof how to change. With this definition of probability, we change from infinite to finite events. Okay, stop here. See you later. Goodbye. Please remember to exercise from 2.1 to 2.48. We have a lot of examples. However, it's not difficult much. So I hope that you can do all of this exercise. Goodbye. The end.
Goodbye, teacher.
Goodbye, teacher.
Bye, teacher.
Dạ,